Welcome to this tutorial. In this tutorial, we look into the effect of the condenser pressure on the thermal efficiency of a simple ideal Rankine cycle. We already have discussed this in previous video, so if you don't know what is a simple ideal Rankine cycle, please watch previous videos. We do this by doing sensitivity analysis is in Aspen Plus program. Let's do this by considering an example. Let's say that we have a steam power plant that operates on a simple ideal Rankine cycle. Steam enters the turbine at 15 megapascal and 600 degrees C, and it's condensed in the condenser. We want to investigate the effect of the condenser pressure ranging from 1 bar to 0.01 bar on the thermal efficiency of this cycle. We assume that the steam flow rate is 10,000 kilogram per hour. Assuming the liquid fraction at the turbine outlet can reach up to 10%, we want to see what is the lowest acceptable pressure in the condenser. Let's work on the same simulation file we did last time for a simple ideal Rankine cycle. We had the vapor at 600 degrees C and 150 kilopascal that enters to the turbine, and then the condenser pressure is set on 10 kilopascal, and then we had a pump and a boiler. Uh, if you remember from the previous video, we set up a simple ideal Rankine cycle by turbine, condenser, pump, and boiler. In the original simulation, the pressure was 15 megapascal or 150 kilopascal, and the temperature was 600, and the condenser pressure was 0.1. And if you remember, we set this outlet pressure of the turbine here in the specification as discharge pressure, and we set the pressure change of the condenser to 0. This means that if you change the output pressure of the turbine, it will be automatically transferred here and it will stay the same. That's why I suggested you to choose this option. Otherwise, you need to change it every time. In order to investigate the effect of the condenser pressure, we have several options. One simple way is to just perform the simulation several times and write down the thermal efficiency of the Rankine cycle and see how it changes. We also have a very useful tool in the Aspen Plus program. If you remember, we last time we did some calculations using the calculator tool. This time we pick the model analysis tools and we select the sensitivity analysis. With the sensitivity analysis, we can vary one variable in the simulation and look into the results of our simulation. So if you click on that, then okay, you create a sensitivity analysis case study by selecting by clicking on new and pressing K. You can name it as you wish. I keep it as S1 sensitivity analysis 1. Here you have several tabs and you need to define your variables. In the vary tab, you need to specify the variable that you want to manipulate. So if you remember, we said that we want to change the output pressure of the turbine. So we click on new and we define a new variable. And let's say it's variable 1. The type is block variable. The block is turbine and it's the pressure of the turbine. So we scroll down and we check, we select the pressure and we keep the unit as bar. The start point, let's say that it's the lowest pressure that is given in the exercise, and the highest is 1 bar. And we can either put the number of points that you want between these two start and end point or an increment. So I put 0.02 as increment. You see this yellow triangle here. It's a warning. It says that the number of points is not an integer. You can solve this in different ways. Either you can pick a different value for the increment. Now we have 100 number of points, or you can directly insert the number of points. Let's, instead of 100 points, let's pick 10 points here. So we pick 10 points as the number of points between 1 and 0.01 bar. And now we proceed to define the variables that we need. You can do it in two different ways. You can click on new and do exactly the same as what we did for the calculator. But let's start with work of the turbine. Let's say that we have the work of the turbine. This is a block variable. The type is block variable. The block is turbine, and it's the work that it's produced. We can pick the power, and the units is in kilowatts. For the next variable, you either can do the same, or you can, if you have already done it somewhere else, you can copy and paste from there. If you remember, we did this in the calculator input, so we had a list of different variables. For example, the work of the turbine. It should be the network, not the power. I will change it later. So you can select the work of the pump and the Q of the boiler, and then you press on copy, and then you go back to the input, and you can insert them here by selecting paste. Here I need to change this the work of the pump is the network, the Q in is the duty of the boiler, and the work of the turbine. I think I need to select the network instead. So network here, and the units is in kilowatts. So we need these three variables in order to calculate the efficiency. So we can do it in the tablet tab here. We do this in one column, the tabulated variable. Let's say that we want to calculate the minus work of the turbine minus work of the pump, and then multiply by 100, and then divided by Q in. This will give us the efficiency of this cycle. Now we are done, and everything is in blue check. So we reset our simulation and we rerun it. Now the simulation is over. Results are available. So if you go to sensitivity analysis result tab, here you see the list of the different values of the thermal efficiency for different pressures that we have selected. If you draw the diagram by clicking on the custom, and then on x-axis, let's select the pressure, and on the y-axis, let's select the efficiency, then you will see such a diagram. So you see, the lower the pressure of the turbine, the higher the efficiency of your cycle is. But remember that we have a limitation. If you go back to the presentation file, in the exercise, it says that the liquid fraction of the turbine can reach up to 10%. And if you remember, the lower the pressure for the condenser, the more liquid you will get. If you look into this TS diagram, if you lower the pressure of the condenser, you move to the next pressure line under this line, which means that if you look into the portion of this divided by the total, you will see that you have more liquid in your output of the turbine. And in this specific case, we say that up to 10% is tolerable by the turbine. So we need to find the pressure that gives us the highest efficiency, and also we won't exceed 10% of the liquid fraction. In order to check the content of the liquid in the output of the turbine, we can add an extra variable here. Let's say that we define a new variable that is liquid fraction, and this is in the streams. The type is uh, stream variable, and the stream is the condenser in, and because condenser in is the stream that goes into the condenser right after the turbine. Uh, and the variable is the liquid fraction. Now we also tabulate a second column, and here we tabulate the liquid fraction of the stream. So now we reset and rerun the simulation again. Everything is done now. We go to the results. Here you see the liquid fraction. So you see up to the, if you start from pressure around 1 bar, up to 0.34, you have no liquid, so you're safe. And after that, you see the liquid fraction starts growing. So we click on custom, and then we can draw the liquid fraction and the efficiency of the turbine. So if the liquid fraction should not proceed like 10%, so we should be somewhere here. So this is 10% liquid fraction. The pressure lower than this will create more liquid, which is not favorable in our simulation. So you see that around 0.22 probably, or 21 is where you want to have your pressure. We can change the range in order to have it a little bit more accurate. So we go to vary, and here we change the values were between, let me double check. Here, let's change it between 0.25 and 0.2. So we go back to the input. So we change this starting from 0.02 and 0.25, and see how these values are changing. So we rerun, and we go back to here. So we see 10% of the pressure around 0.2 is almost the border that we can have to not to have actually the liquid fraction that is dangerous for the turbine. So we can draw the diagram of the efficiency and the liquid fraction. And you see here the liquid fraction is this axis. So 10% is around here. So the pressure is 0.205. So let's say that we pick 0.21 to be on the safe side. Thank you very much. We proceed in another video to do more simulations.